Hi everyone, so this is quiz 4. Okay, so the first problem asks us to find the eigenvalues and corresponding eigenspaces of this matrix, and then to describe each eigenspace as a geometric object and give a basis for the eigenspace. What dimension is this eigenspace? Okay, so first of all, I just wanted to say I know some people struggled with the algebra for computing the eigenvalues here. So I'm going to give you, I'm going to start computing the determinant, and I'm going to give you a pointer as to how to keep your algebra simple so you don't get to a point where you have to factor a cubic polynomial. Okay, so to find the eigenvalues, we're going to find the roots of the determinant of 3 minus lambda 2, 4, 2 minus lambda 2, 4, 2, 3 minus lambda. Okay, so I'm going to write this out, and then I'm going to tell you how much simplification I'm going to do, and specifically some simplification I'm not going to do. Okay, so 3 minus lambda times, okay, now I'm going to multiply this subdeterminant, so I get minus lambda times 3 minus lambda, and then a minus 4. I'm going to have minus 2 times, here my subdeterminant is 2 times 3 minus lambda minus 8. And then finally plus 4, 4 minus a minus 4 lambda, which is plus 4 lambda. Okay, so at this point I have a few options. What I could do is multiply out this quadratic and then multiply this in, ending up with a cubic, simplify everything, and I'd have a cubic polynomial, which I'd be able to factor, but probably not very easily. So the thing to do when you get to this point is don't combine too many things. Okay, so what I'm going to do is I'm going to leave this 3 minus lambda sitting here. I'm going to multiply out and simplify this quadratic. I'm going to simplify each of these binomials as much as possible, but I'm not going to combine things unless they're just obviously must be combined. Okay, so what that looks like, I'm going to have a 3 minus lambda times lambda squared minus 3 lambda minus 4. Okay, now I get a minus 2 times 6 minus 8 is negative 2 times minus 2 lambda. I'm going to factor a 4 out here, and I'm going to get plus 16 times lambda plus 1. So I factored out the 4, and I get a 1 plus lambda. I reordered it, so it's lambda plus 1. Okay, I'm going to do one more step of simplification. I get 3 minus lambda times lambda squared minus 3 lambda minus 4. Now here I'm going to factor out a minus 2. So I get a plus 4 lambda plus 1 plus 16 lambda plus 1. Okay, now I don't want to simplify too much. These things obviously I can add because they're just copies of the same binomial. I don't want to multiply this out though, because actually when I do that I lose some nice factorization I was already given. I already know that 3 minus lambda divides this cubic polynomial, so I'm going to use that, and instead I'm just going to factor this quadratic polynomial, because factoring a quadratic polynomial is quite a bit simpler. So when I do that I get 3 minus lambda times lambda minus 4 times lambda plus 1. Now I end up with a plus 4 lambda plus 1 plus 16 lambda plus 1, so I get plus 20 lambda plus 1. So one thing to notice is that I got the same binomial factor sitting here, lambda plus 1, in my the second parts of my cofactor expansion contributed a lambda plus 1. And here, when I factored my quadratic, which was the simplification of my first subdeterminant, I could factor that quadratic and get out a lambda plus 1. So I get the same factor from both the quadratic subdeterminant and the other subdeterminants. Okay, now the reason that's important is that now I have something that I can very easily factor. So I'm going to factor out lambda plus 1 from the total from each of these pieces. So now I have lambda plus 1. I'm left with 3 minus lambda times lambda minus 4 plus 20. Okay. So I used all that information so that I could factor out a lambda plus 1. Now I'm going to multiply this out and simplify it because it'll become a quadratic, which I can handle. I don't ever want to go up to cubic if possible, but right now this is just a quadratic, so I can multiply it out and leave it as a quadratic. So I'm going to get a minus lambda squared. I get plus 4 lambda plus 3 lambda is plus 7 lambda minus 12 plus 20. So lambda plus 1 times minus lambda squared plus 7 lambda plus 8. Now I want to factor out this minus so that I can factor this really easily. Lambda squared minus 7 lambda minus 8. And now I see I can factor this quite simply. So it's minus lambda plus 1. Now here, the factors here are a lambda minus 8 and a lambda plus 1. Okay, so I see that I have two eigenvalues. The first one is lambda 1 is equal to negative 1, and I get that with multiplicity 2. The second one is 8, and I just get that with multiplicity 1. Okay, so now we need to find the eigenspaces. And I just want to reiterate too, so the idea here is when you do your cofactor expansion, don't immediately start simplifying as much as possible. Just simplify things that will stay quadratic, okay? Then once you have them to quadratic, use the fact that you can factor them so that you can then simplify again until you have something where you can easily factor into the three pieces. So you should practice that on some other matrices, but when I design these problems, I always choose matrices where this same binomial will pop out here and here, and it also will come into this subdeterminant quadratic polynomial. Okay, so for lambda 1 equals negative 1, I need to find the eigenspace. So I subtract this lambda on the diagonal, and I get 4, 2, 4, 2, 1, 2, 4, 2, 4. Okay, so I'm solving that equals to 0. So both of these are just multiples of this row. This is 1/2 of the first row. This is just 1 times the first row. So those will go away, and I'm going to divide the first row by 4. So I get 1, 1/2, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. So now I can write down the solution set and the eigenspace. So the eigenspace is C times negative 1/2. I negate this row and put a 1 in the second entry. I negate this, I meant column. I negate this column and I put a 1 in the third entry. Okay, so we see that this object is a plane and it is two-dimensional. Now the basis for this eigenspace are just these vectors. They are linearly independent. So I get minus 1/2, 1, 0, negative 1, 0, 1. Okay, so that's my basis for this eigenspace. This eigenspace forms a plane. There are two linearly independent vectors, so it spans a plane. And notice this is the span of two linearly independent eigenvectors. That's the eigenspace. And because the basis is of size 2, and because we know a plane is two-dimensional, we see that this is two-dimensional. Okay, so now for lambda equals 8, I subtract 8 from the diagonals. I get minus 5, 2, 4, 0, 2, negative 8, 2, 0, 4, 2, negative 5, 0. Okay, just to start off, I'm going to divide each of these rows so that there's a 1 in the first entry. So I get 1, negative 2/5, negative 4/5, 0, 1, negative 4, 1, 0, 1, 1/2, negative 5/4, 0. Okay, now let's zero out these two entries using the first row. So when I do that, I'm going to take this row and I'm going to subtract the first row. Okay, so I get okay, so 1 minus 1 is 0. Now minus 4 minus a negative 2/5. So this is minus 20/5 plus 2/5, which is minus 18/5. Now 1 minus 4/5 is 5/5 plus 4/5, which is 9/5. 0. Okay, now I have 1 minus 1 is 0. 1/2 minus negative 2/5. So this is 5/10 plus 4/10, which is 9/10. Then I have negative 5/4 minus negative 4/5. So negative 5/4 is negative 25/20. And then I'm plus adding 16/20. So negative 25/20 plus 16/20 is negative 9/20. Okay, so one more step. Okay, so I'm going to, so first of all, notice that this right here, so going from negative 18/5 to 9/5, 9/5 is negative 1/2 of this negative 18/5, and 9/20 and negative 9/20 are related in the exact same way. So negative 9/20 is negative 1/2 of 9/10. So these rows are multiples of each other, so I know I'm going to get a row of all zeros if I add them, or the appropriate combination of them. Now I'm going to also divide this first row by negative 18/5. So I'm going to multiply by negative 5/18. So I get 0, 1. Okay, so when I flip that fraction over, I'll get negative 9 times 5 over 5 times 18. The 5's cancel, the 9 cancels, and I have negative 1/2. And then, of course, still the same first row. Okay, so one more step. Okay, now I'm going to use this one to zero out this negative 2/5. So I get 1, 0, negative 1. So I have negative 4/5 minus a negative 2/5 of 1/2, which is negative 1/5. So negative 4/5 plus negative 1/5 is negative 1. And then 0, 1, negative 1/2, 0, 0, 0, 0, 0. Okay, so now my solution set is C times, we negate this this third column, 1, 1/2, and then we insert a 1 in the third entry. Okay, so a basis is just, there's only one linearly independent vector in this eigenspace, so it's 1, 1/2, 1, just this vector. Now this set forms a line, and it is one-dimensional. A line is one-dimensional. We also see that the basis tells us that this is one-dimensional. Okay, so the second problem says, I was looking at a linear transformation L, and I found that when I represent vectors in the standard basis, the matrix which represents L is the matrix A sub L. I found out that the eigenvalues of the matrix A sub L are lambda sub 1 equals negative 2 and lambda sub 2 equals negative 4. The eigenspace associated with lambda sub 1 equals negative 2 is this set, and the eigenspace associated with lambda sub 2 equals 4 is this other set. Okay, so lambda equals negative 2, lambda equals 4. Write down the eigenvectors of A which form a basis for R3. Name this basis B. Is this basis orthogonal? Okay, so the basis of eigenvectors, we're going to take these three eigenvectors and we should check that they're all linearly independent, and they are. 1, 1, 0, negative 1, 0, 1, 1 half, 1 half, 1. Okay, so there's my basis of eigenvectors. If I wanted to check that these were linearly independent, I could smush them together into a matrix and check that that matrix has row-reduced echelon form with one pivot per column. That would tell me that those three column vectors are linearly independent, which means they form a basis since there are three. Is this basis orthogonal? So that's what we covered today. So orthogonal means that they are perpendicular, or the way that we can tell if two vectors are orthogonal is if their dot product is 0. Let's just look here and see if the dot product of every two of these matrices will be 0. Every two of these vectors will be 0, and it's not going to be because, for example, consider 1, 1, 0 dotted with negative 1, 0, 1. So this is negative 1 plus 0 plus 0, which is negative 1, which is not equal to 0, so this is not orthogonal. Okay, the second question asks, is the matrix A diagonalizable? So we know a matrix is diagonalizable if there is a basis of eigenvectors. So in part A, I told you the answer to this one. I said write down the eigenvectors of A which form a basis. So there is a basis of eigenvectors, so yes, the matrix is diagonalizable because there is a basis of eigenvectors. If you expand vectors from R3 in the basis B, the matrix A no longer represents the linear transformation L. What is the matrix D which represents L when input and output vectors are expanded in the basis of eigenvectors B? Okay, so on Wednesday, most of what we talked about was this idea that when we switch from representing our vectors in the standard basis to representing them in a basis of eigenvectors, our linear transformation goes from being represented by a matrix that has no nice structure to being a matrix that's diagonal. And the diagonal entries are just the eigenvalues associated with the eigenvectors. So the diagonal matrix here in this case is just going to be have the eigenvalues on the diagonal, and the eigenvalues occur in the order that we ordered the basis. So I chose that the basis would go 1, 1, 0, negative 1, 0, 1, 1 half, 1 half, 1. So I need to find the eigenvalues for each of these vectors and then put them in the corresponding places in the columns of D. So since 1, 1, 0 goes with lambda equals negative 2, my first column contains negative 2. My second column is also, my second vector is also an eigenvector with lambda equals negative 2, so I get another negative 2. Now this last one is with lambda equals 4, so I get 4, and then it's a diagonal matrix. Okay, the fourth question asks us, what is the change of basis matrix P, which changes from the standard basis to the basis of eigenvectors B? So the nice thing, another nice thing about the standard basis is that when we're looking for the change of basis formula from the standard basis to any other basis, to find the change of basis matrix, all you have to do is smush together the new basis vectors into a matrix, and that's your change of basis matrix. So if we're going from the standard basis to a new basis, just take those basis vectors and smush them together into a matrix. That's your change of basis matrix. So here, our change of basis matrix P, like I say, we're just going to take these column vectors, smush them together into a matrix, and write them down. So 1, 1, 0, negative 1, 0, 1, 1 half, 1 half, 1. That's our change of basis matrix. And then finally, we know from class that D is P inverse A sub L P. Okay, so why does this make sense? So notice D represents our linear transformation in the basis of eigenvectors. So let's call that basis of eigenvectors, oh, we already called it B, sorry. So we'll have B and we'll have the standard basis. So the idea here is that if I give you a vector that's represented in our new basis of eigenvectors b, and then I hit it with d, I get out another vector that's still represented in the basis of eigenvectors b. Okay, so d applied to a vector in b, a vector represented in b, is still a vector represented in b, but it's had the linear transformation applied to it. Now we want to check that the exact same thing happens if we apply this matrix. So in other words, we want to make sure that the linear transformation happens to the vector and that the vector starts in the basis b and ends in the basis b. Okay, so what does p do? P takes in a vector, so on the right side you would multiply p times a vector that is represented in the standard in the eigenvector, in the basis of eigenvectors b, and then we get out a vector that's expanded in the standard basis. We hit it with a sub l, because that applies the linear transformation to a vector that's expanded in the standard basis. And we get back out the image under the linear transformation of a vector, but represented in the standard basis S. And then P inverse maps us back to the basis B. So we hit it onto a vector that's expanded in the standard basis, and we get out one in our basis of eigenvectors. Okay, so I'm going to represent this by putting little letters on the right and left hand sides of these matrices to say that if I'm multiplying this matrix D on a vector, what kind of vector should it be? Should it be expanded in B or S? So D will be multiplied on the right, D times a vector. That vector will be expanded in B, and we'll get out something that's also expanded in B. Now P, we hit something that's expanded in B, we get something that's expanded in S, then our linear transformation is applied and we have something still in the standard basis, and then P inverse takes us now to a vector that's expanded in B. Okay, so notice the same thing that we wanted to have happen here happened over here. So I have a vector expanded in the basis of eigenvectors. I apply the linear transformation, and I still get something expanded in the eigenvectors. Here I go, eigenvectors to standard basis, apply the linear transformation, go back to the basis of eigenvectors.